Not sure it's going to fit.
I got it. No. 4,
You guys are stealing like all my radii. Be creative. Noah.
6, 330.
Okay. So 6, 330. All right, Noah, walk me through. What am I going to do?
Oh, so you're going to draw the graph and then draw 6 lines.
Okay, so I need 6 tick marks. So I need to go one more. One more. One more. And one more. Okay, now what?
And then draw the circle.
You want me to draw the full circle? Okay.
No, just one on the 6 part.
Okay. So I'm doing. Now, guys, technically, this is not bad, but do I have to actually draw the full circle? Okay, you don't actually have to draw the full thing, but that's okay. We can visualize with the full thing. So now what do we do?
And then go to where 330 degrees is at.
Okay. So I have 90, 180, 270, 360, a little bit less, right?
Yes.
Now what? Where the two intersect. Does that make sense? So if you get to an angle line, does anyone remember the snazzy name from that from yesterday, the angle line? Close. Radial line. When we get to the radial line for 330, we look first of all at the 6 and say positive or negative, and the 6 is? Which means 330, we like that guy, so where are we headed? Towards him. If it was a negative, we don't like that guy, so where are we headed? Away from him, okay? And then for the 6, we're not thinking right 6, we're not thinking down 6, we're thinking kind of both of them. Around 6, sort of, right? Around 6. So when you're doing polar, find the angle, think, am I going towards or am I going away? And then you have to think with the XY plane, not right 1, not down 1, not left 1, not up 1, but thinking, okay, what if I was to go out 1, out 2, out 3, radii, out 4, out 5, out 6. And no, that's why I was saying you actually don't need to draw the whole 6, which is totally fine that we did. Because you could just think going out 6 and then just as you curve around, say, hey, where will it intersect? Very cool. So do we actually need the snazzy polar graph? And the answer is no. But does it help? Yeah, it does. But you're not going to probably have it in your, well, you're definitely not going to have it in the homework, and you're not going to have it on any other graphs and notes, but you might have one on the quiz all nice and drawn for you. Michael, go ahead. They'll be mostly small. But they could give you something exciting like, and I don't think we did this yesterday. Let me give you one last one. What if I was to give you negative 1.7, 213. Take a second. Remember, tick marks on an X and Y, they just give us like little boundaries, but we still approximate with decimals or fractions or weird. So think, how would you approximate in polar? Negative 1.7, 213. Take a second. Where would you put it? Leo, why aren't notes open, bud? We've definitely started for quite a while now. We're in our notes. No homework is due today, so we're definitely not doing that. It's pretty self-explanatory, bud. I know that Ruth is in her AP Spanish exam, right? Rest in peace. That was encouraging. Good thing she didn't hear it. And then we have Jacob, who's gone today. And then Jaden's still gone. He was gone yesterday, too. If you were to think of the old-fashioned rectangular quadrants, kiddos, what quadrant would this point be in?
1.
Do we like 213?
No.
So where are we headed? Negative. Negative 1.7. We're headed away from 213. Where would 213 be? Well, here's 180. Isn't this one 210? So we have 210. We have 225. So we would go just a little bit past 210, but I'm not going there. I'm going the other direction. And I'm going negative 1, negative 2, and somewhere just a little bit in between. What do you guys think? Pretty close? So instead of heading towards 210, a little bit past, I'm headed towards 30, A little bit above. Ooh, that's on. Lo siento. Yeah, I apologize. That shouldn't be on. The 30 degree. That should be just a little bit above the 30 degree. And here's my 2. It's a little bit below. There we go. So it needs to be in between the 30 and the 45, in between the 30 and the 45, and in between the 1 and the 2. But 1.7 would be closer to the 2 than the 1. So yeah, we can even do decimals in polar, just you're going to have to think about going in between the radii for something like 1.7. Negative just meant backwards. And then the 213, you have to think about going in between the radial lines for your angles. Okay, so that's just kind of like, can you graph points? Yes. Polar's a little harder than parametric, right? Parametric said, give me a t, I'll give you an xy, and you're like, psh, I can do xy's, I've done that before, right? Polar's like, haha, r theta, and you're like, what? Who's r? Who's theta? What's a negative? Okay, so we had to kind of talk about, ooh, how do I even do the graph, right? That's a little bit messy and a little bit nasty, but I think we have a good idea. AJ, go ahead. Yeah. Yeah, for the quiz. It's not a test. Yeah. Where what was in decimal points? Yeah. Remember, the only thing that you've been required to do by hand all year with angles have been unit circle angles. Right? So if there was something with decimals, then you'd be fine. You wouldn't be expected to do that by hand. You'd be able to use your calculator. Kind of like probability, how you were able to have your calculator the whole time. Kind of like conic sections, how you were able to have your calculator the whole time. On the quiz, yes, you are able to have your calculator the whole time. Here's the dilemma. Could you have had your calculator and known perfectly how to use it on the conic section test and still messed up? Vicky, phone away. Vicky, phone away. I don't want to have to take it. Thank you. You could have still done horribly on that test. Why? Was the calculator enough? So that's my warning. The calculator is not enough, even for the polar and parametric, but yes, you will be able to use it. But if I was to give a problem like, hey, make a table and graph, sure, you could check it on your calculator, but to get full points, you would need to make the table and graph. Does that kind of make sense? Okay, perfect. Good question, though, AJ. It's good for people to plan ahead, right? Converting. We converted in parametric mode from in terms of t to out of terms of t, but we didn't really call it conversion. I did. I called it conversion a couple times, but the book called it eliminate. Remember our sniper? Remember getting t by himself? Erasing his identity? We were getting rid of t. We were getting out of parametric, and we were getting into function mode, y equals f of x. We were getting rid of t. Or we were taking y equals f of x and we were putting in t, and we were going from rectangular to parametric. So the wording was way different in parametric. It was eliminating the parameter or solving or finding parametric equations. But in polar, for 10.7, it's going to be super obvious in that we're going to talk about converting, which is technically what was going on in parametric. But to convert in polar, we need more than just algebra. We need more than just, solve for and plug in. Get a loan and substitute. We need more than that. And the reason is because x's and y's don't automatically come up in polar. And x and y is still kind of there, the idea going over and going up to a certain point that you might have. But the problem is in polar, that point, even though you can go x and y to get there, in polar, we don't go there horizontal, vertical. We go there turning an angle and going out a radius. We don't go there in polar by going to the right and going up. We spin or we rotate an angle and we go out a radius. Now the interesting thing is we've definitely seen this triangle many times this year. And the one that's going to help the most for this section is when we saw it with vectors. Because with vectors, instead of just going horizontal, vertical to a point, we would turn an angle, we would go a certain direction with a certain magnitude. Magnitude direction, super similar to r and theta. Just different application. Now, guys, technically, there are these like, hey, you could be going from polar to rectangular, or you could be going from rectangular to polar. You could be going from some sort of r equals f of theta to some sort of y equals f of x, or we could be going from some sort of y equals f of x to r equals f of theta. So one way is you have r's and thetas, you're trying to get to x's and y's. The other way is you have x's and y's and you're trying to get to r's and thetas. And in years past, I've kind of just put formulas in certain categories and said, oh, this one's always nice for this direction and this one's always nice for that direction. But the problem is that's not always true. You can get something weird, you can get something out of the norm, where you might have to use maybe one of the equations I would have put in this category to do this type of problem. So to not limit you, I'm just going to give you all the equations in a kind of particular order, but still in a way that can hopefully help without necessarily putting them in a certain camp that might limit you when you go to try to do some of these problems in homework. So let me give you the most obvious one. The most obvious one is x squared plus y squared. Hey, what theorem am I using? Pythagorean. X squared plus y squared is going to equal what? R squared. Yeah. So that's one of the most basic relationships. If you have x and y, you can get to r just by using Pythagorean theorem. And real quick, these formulas aren't just helpful when going from a certain equation in polar to a certain equation in parametric. Sorry, not parametric, in function or rectangular. But it's also helpful when going from an r theta. If you're just converting points, you could convert equations, but you could also convert points. So there are different things they might ask you to convert. Maybe equations, but maybe also points. Just a quick heads up. So we have x squared plus y squared equals r squared. Let's see. What's another formula that uses x and y and can somehow get to r theta? Well, we already got to r using the sides. Now what if we take x and y and try to get to theta?
Tangent of theta equals y over x.
Tangent of theta. If we divide y by x, then we'll know what the tangent of theta is. And so if you guys look at that, tangent of theta equals y over x, couldn't we take this guy? And couldn't we maybe do a little theta is going to come from tangent inverse of y over x? Now, I put a colon, not an equals, for a very, very, very particular reason. Because tangent inverse, as we've talked about many times this year, the function in your calculator only goes between negative 90 and 90. But as we've seen, these polar points can be in the second quadrant, can be in the third quadrant. So I'm going to write the note that I've written several times this year. Check the location. Check the location of the original point that you have. If it's a point, check the location. And the reason is you might need to add 180. You might need to add 180. Bless you, bless you, bless you. We've seen this come up several times this year, where tangent inverse gives us one angle in the fourth quadrant, but my actual location is in the second quadrant, so I need to add 180. Or my tangent inverse gives me a location in the first quadrant, but I actually need in the third quadrant, so add 180. So that's why I say check the location. Where should it be? Compare it with the answer that you're getting maybe in your calculator for what AJ was saying, a weird decimally non-unit circle answer. You might need to add 180. Okay, so we have those two equations. We have x squared plus y squared equals r squared. We have tangent of theta equals y over x. But what if we aren't given x's and y's trying to get to the thetas and the r's? What if we're given r's and thetas to get to the x's and y's? In that case, we're going to want a couple different equations. Let me just write them down real quick. But yeah, I think AJ, you already found them. X equals r. This looks a lot like vectors. And y equals r. It's like when we were changing from horizontal or from components to angles, directions, and magnitudes. Or taking directions and magnitudes and getting to components, horizontal, vertical components. These formulas you guys have basically seen before. You just didn't call this first piece r before. We called it magnitude cosine angle and magnitude sine angle. But now in polar, it's going to be the radius. That's the hypotenuse of my triangle, my right triangle. Now I could go ahead and come up here and say like, oh, why is that true? It's true because cosine of theta So ca would equal adjacent over hypotenuse. Or sine of theta, so, would equal opposite over hypotenuse. And what did this formula do? It said, hey, I can solve for x by multiplying by r. Or hey, I can solve for y by multiplying by r. So these formulas come right out of SOHCAHTOA. It's just it might be a little faster. It might be a little easier if you just memorize them. Or you have them written out in the nice form to plug in. Now, these are the relationships. These are the formulas that come out of, or that compare, that relate, polar with rectangular, rectangular to polar. So let's go ahead and do some practice. And I think for some reason these questions always disappear in my notes. So let me get the ones out that we're going to look at. Let me keep these formulas up. Let's see if I can kind of dual screen it. All right. So for example, coordinate conversions. Coordinate, that's like an ordered pair. Coordinates, just like an x and a y, an r and a theta. So we're not going to equations yet, just coordinates. So that's in this first category of r theta to xy, or xy to r theta. Now, this first one. If it says from polar to rectangular, what are you starting with? What kind of point? Which case is it? From polar to rectangular. Start with the polar point. Start with the r theta, and you're going to rectangular, xy. Whereas this one says start from the beginning point, xy, to r theta. So sometimes that's helpful for your brain to kind of realize before you even start the problem. Then let's check out what's number 12. Number 12 gives us the point of -3, 11 pi over 6. Now, I think it's always a good idea because of this little scary note right here about how the calculator might give me an answer and I might need to actually visualize the graph. I think it's a great idea just to quickly think of, hey, can I figure out where this guy is? Guys, what quadrant would 11 pi over 6 be in? Good, it's almost a 2 pi, right? 11 slices cut into 6, that would give me one whole calzone and a little bit more. So here's my 11 pi over 6. The problem is, why am I drawing the graph or the line both directions? It's negative. So I'm going to go -1, -2, -3, curving around. Do you guys see why I put the point right here? So curving around that circle with a radius of 1, radius of 2, radius of 3. Okay, that's where I want it to be. All right, cool. What's the x's, y's? Left a little bit, up a little bit. Left 2 point something maybe, up 1 or 2 point something maybe. Sure, that's a horrible answer. So how are we going to get better than that? Look at your formulas. Do you see any one that you could plug in 2 things to solve for a third thing? I need 2 to be known and 1 to be unknown. Well, see, if x squared plus y squared equals r squared, that's a good formula, but check it. Don't I just have an r and a theta? So can I plug in both of those to this formula to solve for a third? No. Can I plug in r and theta? No, I'm going to have 2 unknowns. 2 unknowns. Ooh! Plug in an r theta and get out of what? Plug in an r theta and get out of what? Psh, let's use those 2 formulas. So x is equal to r cosine. Y is equal to r sine. Now, AJ, on the quiz, you could plug this into your calculator. Just make sure you're in what mode? Radians, 11 pi over 6. But technically, some of you might be able to do this just a little bit faster if you think over a lot and down a little. Maybe you could save some time on this one, because cosine is going to be √3 over 2. Sine is going to be -1/2. So you'll end up with -3 √3 over 2, and you'll end up with +3/2, which ends us at the point x. Remember, we put the 2 coordinates together. We put the ordered pair, or we state the entire ordered pair. So 3 √3 over 2 and 3/2. 3 √3 over 2 and 3/2. So if I was to zoom in on this picture right here, 3 √3 over 2, can someone throw that in their calculator real quick? What's that decimal? 3 times rad 3 over 2? I'm thinking it's going to be 2 point something something, -2 point something something. And then 3/2, we know that one's 1.5. So does it make sense that you go negative 2.59 something something and then up 1.5? Hey, I actually did a pretty good job graphing that time. Because it does look like my point is negative 2 point something and positive 1.5-ish. Cool. So the point makes sense with the original point. So yeah, I'm pretty sure I got there as long as my math was right. Now, what's different when we get to number 54 and it says, hey, let's go from rectangular to polar now. Let's go the other direction. And they give us the point negative rad 3. Rad 3. This is no longer an r and theta that they've given us, right? Because of the directions. What did they give us instead? Exactly. So then, check it. Leo was saying x and y. Go look at those formulas. Which formulas are going to help if we have x and y to plug in, and we're going to get out something else? Do you guys see how this is so much more useful now? I have an x, I have a y. Sweet, let's plug it in. So I need x to be squared. I need y to be squared, and I'll get out r squared. So I can plug in that negative rad 3, plug in that rad 3. Any square root squared will just simplify down to be the original. So isn't r going to equal square root of 6, which can't be simplified? Yes. But I'm not done, because I need r and theta. That's okay, though. Any other formulas that say, give me your x and your y, and I'll help you get to theta? Yep, tan. So I can say tangent of theta equals y over x. My y is my second one. My x is my first one. Oh my goodness. I'm pretty sure I'm supposed to know when tangent equals 1 or negative 1. Square root of 3 over 3, 1 square root of 3. 1 happens right in the middle. What angle's chilling right in the middle? 40, 45s, right? 30, 45, 60. Square root of 3 over 3, 1. Wait, but I need negative 1. If I was to plug this in my calculator, someone in your calculator, plug in tangent inverse. Tangent inverse of negative 1. Tangent inverse of negative 1. If I were to take tangent inverse of both sides. Yeah, negative 45. Why? Well, isn't tangent negative in the fourth quadrant? All students take calculus. Yeah, tangent's negative in the fourth quadrant. So did it give me a place where tangent is negative 1? Yeah. But I don't need a place. I need the place. Ugh. I don't need a place. I need the place. What did we not do that we did with the other point a second ago? We didn't visualize it. We didn't visualize it. All right, it's an x and a y. So if we're visualizing, cool kids, if I have a negative x, I'm headed what direction? To the left. Whew. And this is points we've been graphing for a long time. So x's, if x's are negative, you're headed to the left. If y's are positive, you're headed up. So therefore, shouldn't it be in this quadrant? Is that negative 45? So what do? Check the location. It's not where I need it to be. Do I need to add 180? And the answer is most definitely. So what is 180 plus 45? So here's the struggle. Tangent inverse of negative 1 did not equal theta, but it was the means to which I could get there. Negative 45 plus 180, or 180 minus 45, and theta ends up equaling 135, or if you're super snazzy like that, 3 pi over 4. Dun, 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 dun. Wait, no! We know r, we know theta, but what were we supposed to find? The polar point. So what did we have to do up here? We took the x and took the y and put them together in an ordered pair. What are we going to do down here? Take the r. Take the theta. And you could do it also in radians. But you got to make your order pair. You got to make your order pair. Bless you. Blessings. So does anything get crazier when they say don't convert coordinates but convert equations? Does anything get crazier if they say don't convert coordinates, just order pairs, convert equations? I'm going to go ahead and slide these formulas down so we can keep on looking at them because maybe they'll be helpful. And then let's go ahead and check out what on earth changes. This is, I think, the last slide of today. We just have a couple examples. Yeah. What changes when they say don't convert just coordinates, convert equations? Now, we're going to have a couple examples of each because these are just a little bit harder. So first of all, going from rectangular to polar. What do you guys think? Is that going to be r's and thetas to x's, y's, or x's, y's to r's and thetas? Okay, good. So I'm trying to eventually get to my r equals f of theta, and I probably have something like a y equals f of x. Sometimes they'll try to trick me, but this is the general idea. So number 75 gives us the equation of, ooh, do I want to start with that one? He's kind of nasty. Let's start with 82. Let's start with 82. You guys can write it in whatever order. You can leave me a little bit of space and come back to 75. 75 is a little funny. I'll show it to you still, though. X equals, I think it's 10. I think it's 10. You can write them both down. If you want to, you can consider them both. Here are two different equations that have x's and y's. They're maybe not the normal, like y by itself sort of thing, but there's still two equations with x's and y's. I want you guys to look at those 4 formulas on the page before. P.S. These 4 formulas, pretty important. Pretty important. Your calculator won't tell you these. Okay, yellow circle. Ooh. Not a yellow box like the conic sections. Joel, we doing okay? All right. Just making sure. So guys, look at those equations. Is there anything that could help us get rid of the x in number 75 and get in r's and thetas, or get rid of the x and the y, maybe all at once, maybe in 2 separate steps, and get in r's and thetas? Any ideas? I mean, we could divide. We could like get y equals, if you want, 1 over 2x. That's okay. But we still have to somehow get in r's and thetas and get out x's and y's. If we isolate the guy, can't we substitute and erase his identity? Right? X is isolated. Y is isolated. It's just ready to get erased, in a sense. It's ready to get substituted in for. So can't I come over here and can't I say, let's get rid of the x and plug in who he equals? What does x equal over here? Isn't the x gone?
Yes.
Aren't the r's and thetas in?
Wait. Are we doing number 75 right now?
Well, I was looking at both of them. What can we do on this guy? Do you think this helped?
No.
Okay, so hold on. What can we do for x and y? Is there a formula with x, y? No. But there is a formula for x, and there is a formula for y. Who's x equal? Who's y equal? Look, x is gone, y is gone. Sweet. We're done. Here's the problem. They want us to, even though it didn't start in pretty form, they want us to end in pretty form. And to end in pretty form, instead of getting y by itself in rectangular, we're going to get r by itself. So how do we get r by itself? Yeah, can't we move the cosine? No, not cosine inverse. We're not getting into theta. We're just getting r alone. So can't we just divide? Yeah, take the cosine and the theta. We can move the whole thing. So 10 over cosine theta. Is this right? Answer, yes. Can I be snazzy and say, haha, it's the same thing as 10 secant? That was a baby T-proof skill, but that's okay. 1 over cosine is the same thing as secant. Anyway, they're both the same equation. They both mean the same thing. Now hold on, wait. How do we get r by itself now? Okay, divide by 2. What else do you want to divide by? Anything else? Sure. Oh, divide by everybody? Because then that guy's going to reduce, that guy's going to reduce, and that guy's going to reduce. Sweet. So divide by 2 and cosine and sine. Yeah, I haven't written anything down yet. But yeah, good. R times r will be r squared equals, ooh, can I make this 1/2 secant theta cosecant theta? Ooh. Oh, that kind of looks nasty though, right? We could have done that. Do you know what else we could have done? Could have also done r squared equals 1 over. Anybody remember the double angle property for sine? 2 sine cosine is sine 2 theta. They're both technically right, and they look very, 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 very different. But we learned with t-proofs that equivalent expressions can look very, very, very different. That's right, that's right, that's right. Wait, is r by itself yet? So technically, we'd have to. So we could say that r is equal to the plus or minus square root of 1 over 2 cosine sine, or all of those are right. All of those are correct. Josh. I'll get you a napkin, and you can definitely, I mean, you may, and I think you can. Leo. Twos cancel out?
Yeah, 2 on the top.
Well, when I divided, it did cancel, but what I do to one side, I also have to do to the other. Does that make sense? So I divided one side and the other side by, those ones reduced. So that 2's gone, but that 2 has to stay. Now, this is a special property that sine 2 theta is equal to 2 sine cosine or 2 cosine sine. That was like a property back in that chapter 5 long list. So the only reason that the 2 went inside was because of that very specific formula. Otherwise, it should have stayed. Good question, though. All right, so that didn't seem too bad, right? Maybe a little nasty because I showed 5 different ways, just kidding, 3 different ways of showing the answer down here, but they're all just as correct. I'm just trying to say sometimes the book might bring in an old formula to make things look a little different, a little differently, I should say. So let's just look at 2 last examples, then we get to go to homework. And some of you might already start writing down the homework if you haven't written it down yet in your homework spiral. But hold on, 2 more examples, because now it's not going from rectangular to polar. Now we're going from polar, some equation with r's and thetas, to rectangular, getting y by itself. So let's see if this gets any harder or any different. We have those same 4 formulas. They're not showing on the screen right this second, but we've been using them a lot, so maybe they're kind of getting stuck in your head. I have theta equals 2 pi over 3 as one equation. That's number 95. There's a theta. Oh, there's not an r? There's a theta, but no x's, no y's. I somehow have to get x's and or y's in there. And then number 109 gives us the equation r equals 2 sine of 3 theta. Let me peek real quick if I actually gave you guys one of these. Basically, I'm going to scare some of you by doing this example. So let's go ahead and, I don't think I gave you a homework problem with 3 theta. It's a little advanced. Let's change this example to number 108, okay? Let's change this example to 108. As you guys remember, we're just doing like an introduction to polar. Let's not go too crazy with that 3 theta. We'd actually have to go back and find 2 different formulas from chapter 5 to help us on that one. Let's go to number 108. That gives us r squared is equal to cosine of 2 theta. Change that example. Let's make it one step easier and one step more practical for what you're actually going to face. Okay. You can look at both examples. Can anyone tell me any formula out of those 4 that might help? We need to get rid of the r's, get rid of the thetas, get in x's and or y's. AJ. Yeah, the only problem is, that's a good formula, but where's tan? He's not there, but what can we always do in math as long as we do it to both sides? We can put something in. We can multiply, we can divide, we can add, we can subtract, we can take tangent of both sides, can't we? We can square root both sides. We can take ln's of both sides. We saw that we can raise to the powers of both sides, like e to the both sides. We can take tangent of both sides, and all of a sudden, life is better, because as AJ said, there's a formula for tangent of theta. What's the formula for tangent of theta? It equals y over x. And not only do we now have the theta gone, but we also, unit circle, 2 pi over 3 is the third angle. Square root of 3 over 3, 1 square root of 3. Square root of 3 goes with this 60-degree angle. Ooh, but that's in the second quadrant, 2/3 of a calzone. All students, sine is positive, not tangent. And I end up with getting y by itself. Y equals negative rad 3 times x. So AJ, going back a long time ago to that calculator problem for the quiz, yeah, you could use your calculator. The problem is your calculator is not going to spit out in nice, pretty form rad 3. It's going to spit out this nasty 1 point something, 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 something. And you'll have to like check in or plug in all the answers and see which one matches up with the 1 point something, 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 which is fine. When it's not a nice one, right? Yeah. And you're like, I wouldn't be able to do that. Yeah. But see, on this one, like if the multiple choice answers have the nice radicals, it might be easier to reference your unit circle, but you can definitely check it, right? You can plug in like the answer in the multiple choice, check it with your decimal. Either way. How about number 108? Good eye on that one. R squared. Ooh, that's an easy formula. R squared anyway. R squared equals what?
X squared plus y squared.
Sweet. R squared's gone. Uh-oh. Chapter 5. Wasn't there a formula for the double angle of cosine? Lainey already looked back, and she's actually looking at that big old long list of formulas that you guys wrote out for Chapter 5, and she saw cosine 2 theta can actually equal 3 things. One of them is cosine squared minus sine squared. Another one is 2 cosine squared minus 1. And another one is 1 minus 2 sine squared. That's back in Chapter 5, the double angle property of cosine. Which one should we use? I don't care. Which one do you want to use? Sure. That's like the first one, right? Cosine squared minus sine squared. And you're like, well, that's disgusting because I don't have anything to plug in for that either. Well, you kind of do, because don't we have a right triangle that all of these different formulas come back to? Doesn't that right triangle have an opposite and an adjacent and a hypotenuse and an angle? So who's cosine of this triangle and who's sine of this triangle? Cosine would be x over. Nice. I got an x, but now I got an r. We'll figure it out. What's sine going to be? Y over r. I still have my little x squared plus y squared over here. Now I can say x squared over r squared minus y squared over r squared. Hey guys, what's going on with the denominator over there? Isn't it the same?
Oh, it is.
What can I do? Yeah, put them to technically subtract, but yeah, put them together, common denominators. You guys know me by now. What do we do if something's stuck in a division? Multiply. Get rid of that division. Wait a minute. Didn't we already have an r squared way back when? And now we have another r squared? No stress. I was able to substitute for the other r squared. I can do the same for this guy. So I end up having x squared plus y squared times x squared plus y squared. Oh, that's funny. Isn't that just x squared plus y squared squared? Do you like all the squareds? He's x squared plus y squared. We already had an x squared plus y squared. Now it's an x squared plus y squared squared equals x squared minus y squared. Now here's the dealio. Some of you are like, oh my goodness. This is going to be awful to get y by itself. You're totally right. Sometimes it's not practical. You're like, seriously? Yeah, it's not practical to get y by itself. Look in the back of the book. Sometimes they don't. Why? Because it would be ridiculous to do so. Whew! Sweet. So we can stop, and the answer is yes. If you don't have your homework written down, go ahead and get it written down. I'm going to show you on the screen in just 1 second, not only 10-7, but also the review. And I'm going to pop up the beginning of 10-7, so once you have the homework written down, you can start doing the homework right away. Leo, go ahead.
Where did R go after?
Oh, I substituted with that spiffy conversion formula that I actually used at the very beginning. R squared, according to our formulas, is x squared plus y squared. So I did it again. Lainey. Yes, you may. Let me show you the two homeworks. Some of you might be able to start, probably not right this second, but start on the review at one point. So let me go ahead and zoom in on this just a little bit so you can see not only 10-7, but also the review. We'll talk about it. Hold on. Hey kiddos, not only is the homework up there, but also the beginning of 10.7. So as soon as you finish writing the homework, if you haven't started, shame on you. I told you to graph points last night. You could actually start working on the homework. The quiz, according to our calendar, has been moved to Thursday for two reasons. Number one, we had a student taking an AP today in this class, and number two, we have a few students taking an AP tomorrow in period 5. So in order to consider them and to give you guys a little bit of grace in the midst of your own AP, eventually, you guys don't really have many until next week, season, and to give us a chance for you to work on this longer homework that some of you didn't start like you should have last night. We're going to go ahead and mostly have a work day tomorrow, going over questions on 10-7 and working on the review. Our quiz will be on Thursday. Sound good? Okay. This is homework number 65. Ooh, ignore the numbering. Somehow the numbering got off. Online, it is correct. This is homework number 64 was 10.6. And homework number 65. Online is now correct. I caught it this morning. The numbering got a little off. So kiddos, what's your goal tonight? Finish 10.7 if you're awesome. Start on the review, but come tomorrow ready to use the time productively. And if you're taking an AP tomorrow, you have grace. They just have a work day. You're still taking the quiz with us on Thursday. All right. So the Chapter 10B quiz, which you are allowed to have your calculators on, but you might want to be studying some of the formulas that we put in the yellow circle, right? Section 10.6 and 10.7 is on Thursday. I'm guessing that we have the homework written down by now, right? Oh. I was trying to zoom in on the page for those people that are working. No, I'm sorry. I tried for today. Thanks for asking, though, in class so everybody could hear that they're not graded quite yet. I'm hoping I have a mission dinner tonight, and then maybe I'll bring it to the volleyball game if I can get out of my dinner early, and I'll be grading it there. Now we have it written down. Chris, you got it? You got the homework okay?
I took a picture of it.
Sweet.